There is something undeniably magical about seeing a small plane climbing gracefully over a mountain range. But to get up there and stay up there requires a beating heart under the front engine cover that is built unlike almost anything else on Earth. People looking to build their own airplanes often ask a very logical question. Can I just put my car's engine into a small airplane? Doing that would be a lot like asking a marathon runner to compete wearing steel-toed work boots. Car engines are exceptionally tough, but they are built heavy, using thick cast metals to survive years of stop-and-go traffic. And in your daily commute, you only press the gas pedal to the floor for a few seconds while merging onto a highway. A plane operates in a completely different reality. To even get off the ground, an airplane engine must be light enough to lift its own weight. Once in the air, that engine is running at near maximum speed, non-stop, for hours on end. And most importantly, it absolutely cannot fail. To fly safely, aviation requires an entirely different baseline for engineering, one where shedding weight and guaranteeing relentless reliability supersedes everything else. If you are ready to learn how these incredible machines actually work, be sure to like this video and subscribe to start your aviation journey with us. Let's step away from the outside of the airplane and take a look at the mechanical components hidden directly under the engine cover. You will often hear aviation engines described as horizontally opposed. What does that actually mean? To picture it, imagine two professional boxers standing back to back in a ring, throwing powerful punches outward at the exact same time. This animated diagram shows exactly how that looks mechanically. Instead of pistons pumping straight up and down like in most cars, horizontally opposed engines lay the cylinders entirely flat. The pistons fire outward, away from each other, in perfect synchronization. The primary benefit to laying the cylinders flat is the engine becomes remarkably slim. Builders easily tuck this flat package inside the narrow nose of a small plane, or slide it into the wings. But there is a second, arguably more important benefit. When those opposing pistons punch outward at the exact same moment, their kinetic energy perfectly cancels out. This design eliminates the violent shaking you would normally get from an engine, which is why you see this layout in widely trusted aviation models like the Rotax and the Jabiru. Think of vibration like a hammer constantly tapping on a wire. Eventually, that wire snaps from the stress, a process called metal fatigue. By smoothing out those shakes, these engines protect the structural integrity of the entire plane. Keeping the plane's structure intact is critical, but keeping the engine running is a matter of immediate survival. If a part breaks while you are driving a car, you simply pull over to the shoulder. If you are cruising at 5,000 feet, pulling over is not an option. So what happens if a part breaks up there? Aviation engineers handle this problem through absolute redundancy. It is the ultimate belt and suspenders approach to mechanics. This diagram of a cylinder from a Jabiru or Rotax 914 engine shows this redundancy in action. Instead of relying on a single critical part, these engines double up. Notice the two separate fuel lines feeding the system, and two completely independent spark plugs igniting the fuel. These systems are self-generating. If the main battery dies mid-flight, the engine internally generates electrical current to guarantee backup spark plugs keep firing. For the pilot, this means an aviation engine operates practically like two separate engines running in parallel. If one component fails, the backup is already doing the work, guaranteeing that a single point of failure will not bring down the plane. Up to now, we have talked about purpose-built airplane engines. But there is a fascinating exception in aviation: actual car engines taking flight. People often ask, can I use a car engine to save money? The answer is yes. A prime example is the Aeromax 100, which actually starts its life as a classic GM Corvair automobile engine. However, you cannot just pull the engine from a car and bolt a propeller to it. The car engine must be completely torn down and rebuilt with massive structural upgrades, most notably a heavy-duty piece of hardware called the integral front bearing. Looking at this schematic, you can see the unique physical stress of flying. A spinning propeller acts like a heavy weight held straight out in front of you, constantly pulling forward on the engine's central shaft with immense force. The new integral front bearing acts exactly like a heavy-duty shoulder brace. It locks around the shaft to absorb all of that massive forward pulling stress, keeping it away from the delicate engine block. Builders certainly use car engines to keep costs down, but they first have to heavily upgrade the metals and add substantial reinforcement. Only then can a standard highway cruiser survive the unique physical pulling forces of flight. When you step back from the schematics, it comes down to the person standing on the tarmac, who relies on this technology. Today we have explored 3 distinct paths to power: engines machined entirely from solid aluminum, high-tech liquid-cooled systems, and heavily rebuilt automotive blocks. Regardless of where they come from, they all share the exact same engineering DNA. They are aggressively lightened, perfectly balanced to minimize vibration, and obsessively packed with redundant backup systems. Every small plane flying overhead serves as a meticulously engineered survival kit, designed from its first bolt to keep its pilots safe in the sky. Thank you for joining us to learn about the heart of the aircraft. Please like the video, subscribe to the channel, and leave your own aviation questions in the comments below for our next lesson.